Okay.
So that's that. Thanks for everybody who came to this lecture. Today we study resonators, continuing on our last subject, which was waveguide. We restrict our domain once more, and we get a closed domain. And the wave problem for this domain is called a problem for resonator. Just for warm up, I will write down solutions for rectangular resonator. But I suppose you already know everything. So we have a rectangular cavity of length L and height H. And I set Dirichlet boundary condition on the boundary. So we solve Dirichet's equation. And we can do the same stuff, separation of variables, and geometry is simple. After separation of variables, we have a model solution. Just sine sinusoidal waves. And what's important that now only a discrete set of wave numbers satisfies the problem. So we also have additional relation here, which is so this problem has solution. It's again a Sturm-Liouville problem, but and again it has only solution for discrete number of k. So probably it makes sense to put the indices here. And what's interesting about this problem is that below some frequency, this problem doesn't have any solution, because all eigenmodes they become exponentially decaying waves. So standard question here, so we have some problem, and to find for each k the solution exists, and the first mode here is just half of sine wave, like in this direction and in this direction. And below this frequency, there is no solutions at all. But this for Dirichlet boundary condition. If we have Neumann boundary condition, we have always zero mode, which corresponds to zero frequency and to a constant zephyr. Okay, this is just it. get to sense, but okay, we have like full system of basis functions. So these modes, they form an orthogonal basis, and we can decompose any wave field in terms of its model decomposition. It's kind of, that's what we need to know to build any field inside this resonator. And what do we do in general case? So this problem doesn't have any like surprise to us. And today I will not discuss some like particular diffraction problems, like we can put a strip here, or maybe remove one of them. But if we remove one of the walls, then it's kind of an open resonator, and things getting, again, they're getting towards normal theory of diffraction. But here I want to use some methods from functional analysis to say general things about resonators. And so general case, and then I will formulate a discrete eigenvalue problem. But yeah, I didn't mention this, but of course what we have here is an eigenvalue problem. So we need this thing, like it's kind of a Laplace operator, and we study the eigenvalues of Laplace operator. And if we find all the eigenvectors, or like eigensolutions and eigenvalues, then we have a solution in this general form. So this is the only thing we care about. Okay, let's have a domain of some simple shape. So let the shape be smooth, maybe convex. I'm not sure about convex, maybe it doesn't matter much. But anyway, we have some closed domain of more or less simple shape. And then again we have a wave equation. And Dirichlet boundary conditions. And so, like, what do we need to find? Find Jupiter and Jupiter. So this one. So this is eigenvalues. This is like a square root of eigenvalue. This is eigenvalue corresponding. So what's the general approach? General approach is to define an associated operator or like functional and study its eigenvalues of this operator or like stationary points of associated function. But of course this thing gets quite technically involved, and I won't be able to talk today like in a rigorous way about functional analysis. So I will consider first a simpler discrete problem, and then I will say what we can say about the continuous one. And indeed, if we have this problem on practice, what we will do is we will solve it using finite element method. Because we have a finite obstacle, we can discretize it. If it's not too big, frequencies are not too high. If frequencies are very high, then we actually consider this thing as an open space, because it will work not as a resonator, just as an open space. But if they are small, we have some resonator properties. And like what I do, I put bunch of nodes. I have some boundary nodes. What I'm trying to do here is to build some mesh on top of our domain. I will just, to be definite, I will build a triangular mesh. So these nodes on the boundary field here should be 0 because I have boundary conditions. So kind of field is fixed in these nodes and they are not part of our finite element problem. And then I draw a mesh, and I will have triangulation like this. Okay, everything is triangular, and for these nodes I will have some, for these 3 nodes for this given picture, I will have some matrix problem. So this is number of nodes m. Okay. So I assume you've heard before about finite element methods. So if we just apply a discretization, weak statement, then we take shape functions, for example, like linear shape functions, and do the integration, we will end up with a matrix problem like this. Where this thing is stiffness matrix, and this thing is known as mass matrix. I won't be writing down any definitions, but you're probably aware this is kind of an I integral over Laplace operator, and this is just a weighting I integral for our functions. Or if we use like discrete analogy, we can think of these things as springs and these things as masses. And then springs are described by stiffness matrix, and masses are described by mass matrix, as it follows from the name. And both K and M are n by n matrices. What else do you know about K and M? I didn't put much details here. Yeah, so it's, so what do you know about K and M? First of all, it's symmetric. They are both symmetric, and M is positively defined. And positively defined is when you take like a polynomial, how it's called, sesquilinear form, x, and this form is positive if x, yeah, is not equal to 0. This is called positively defined, and this property is needed to build some nice decompositions. But what we should notice, this is actually not a classical eigenvalue problem for from linear algebra, because from linear algebra we will only have matrix on the left. We kinda can multiply by this matrix, but if we do multiply, we will use all these nice properties. So for example, the resulting matrix won't be symmetric, which is not nice. And then we won't be able to say much about eigenvalues, but we will deal with this problem later. And this is a statement. What I want to study today is this problem and knowing these properties, these nice properties of matrices. Also, second property is symmetric. I want to build some estimates for the first eigenvalue of this problem. And I will do it using Rayleigh quotient. Rayleigh inequality. But before I do it, I need to introduce some theory and to prove some theorems. Any questions? It should be simple to this point, but now it will get more fun. Point 3 in my lecture notes. Actually, I spent a lot of time memorizing how to spell Rayleigh. I hope I am doing it correctly now. So, consider a matrix A. Let this matrix be Hermitian. A equal to I will use the side A cross. It's a Hermitian conjugation. Do you know what it is? Good. I will write it for somebody who doesn't. So, first we complexly conjugate matrix and then we transpose it. And let it be of size, let it be n by n. Now we consider an eigenvalue problem. Ax equal to omega x. So, and let for definiteness x be a vector from Cn. And what properties do we have? Do we know? That's something you should know from linear algebra, and probably if you forgot, it should be very easy to Google these things. So first of all, well, since this matrix is Hermitian, eigenvalues are real. And we can build kind of non-decreasing sequence of eigenvalues. So we can just order them. And this is one property, and second property is that we have n different eigenvectors. And this is a very important thing. So if we have n different eigenvectors, then we can build the basis. And here, well, like here, I suppose that some of them can coincide. So I'll like eigenvectors should be orthogonal, and orthogonality means the following property: J is not equal to m, but from to be general, lambda g and lambda m can coincide. So, like, for example, I can have an eigenvalue of order 2 which has two eigenvectors, but these eigenvectors are orthogonal. And from this, it means that xj forms an orthogonal basis on Cn. It's nice. So, what do we want to prove? As I promised to Giacomo, we will have a proposition. It's either referred as Rayleigh quotient or Rayleigh inequality. And just like this. And lambda 1 is, this is smallest. Smallest. Also, what should I say? If we go from x to beta x to bx, nothing changes. So we can multiply by a constant, it doesn't. And so this is something we want to prove, and probably should we discuss it? Or should we prove it? So what we do, we take any x from Cn, and then for any x from Cn, lambda 1 will be smaller than this thing. And this is a way to estimate the first eigenvalue. So you can take an arbitrary x that belongs to Cn, and then you will get some estimate. And of course, it depends how nice this estimate will be, but still. And of course, you will get the minimum when you take x as eigenvector. And what else I need to say? So this is how this quotient looks for this very simple problem, but we consider it in general case for like wave equation or some integral operators. We usually write not minimum, we write or infimum. More precise thing would have been to write infimum. And I hope you know the difference between minimum and infimum. Do you? The difference is like this. So it's, here the minimum belongs to the space to which belongs x. But that's possible if we take x from one space. It's actually the minimum doesn't belong to the space. So it's the infimum, it can belong to another space of functions or vectors. And then they do not coincide. But here, since they coincide, it's the same thing. So it's just being more precise. More formal. Okay, let's go. It should be not hard. Expand for arbitrary x. So we have an orthogonal basis, and we should use this fact. Then it means that we have the following expansion, which I would have called a model expansion if it was for wave problem. Model expansion. And then for quotient we have this is a sum of positive 6. Yeah, all these eigenvalues are actually positive. And this is also a sum of positive 6. And obviously we have, so we can estimate it just using the first eigenvalue because it's the smallest one. We have an estimate. So it's bigger by definition if we replace all lambda n by lambda 1. thus if we substitute this estimate here, but do you understand why we have this one? This is we just expand, then we applied a here, and axn gives us lambda n xn. Thus we get from this one this. This is the Rayleigh or inequality, and to finish the proof, we just notice that we get the equality when x y is equal to x1. What is it? So how we actually use this inequality? There is a couple ways to use it. One way what we did here is we set up an optimization problem. So we can just take a big set of vector x and then find the minimum vector. And if we do it, then we be able to find number one. This is one way. And another approach is more analytic. We just construct a function which a good guess for the solution of our problem. So we construct a function, for example, that satisfies our boundary conditions, behaves like a wave, but not a solution. But we substitute this function, and this function will give us an estimate for the first eigenvalue.
The estimations will depend on that.
Yeah, it depends. Yeah, it depends. It's kind of yeah, it depends, and usually we have some threshold in mind, and we want to have this. We want to prove that we have, for example, wave modes below the threshold. If, for example, we can prove that we have an eigenvalue that, like, below the zeroth mode for Dirichlet waveguide, then we can prove that we have a trap mode, because this mode won't be a propagating mode anywhere. And this is one way to find some weird modes, and I will talk about this later. But yeah, to find how good is this estimate, you need to do some additional study. It's like a first guess. So what else? Okay, what happens for other eigenvalues? I will write a general theorem. General theorem is known as Courant-Fisher minimax theorem. That's you could have heard about, but it's like when you go to a conference about waves and you meet functional analysis people, they usually mention some minimax theorem. So I will unravel the mystery, and now we will. And again, as was promised to pure people of our department, we have our theorem. And I know how to spell Courant, Fisher, minimax. Okay, this thing looks tricky. I will give you 5 minutes. I should. I also didn't clarify annotation. So this thing is arbitrary some space CM of CM of it probably looks very nice green chalk on green bottom. Not too bad. Of size P. So I will give you 5 minutes to think about it. Let us have a break, and then I will comment on this expression.